In this lesson, we see how faulty genes coding for faulty enzymes can lead to sickness. Isabella joins her friends in sipping wine during a dinner party. As the meal progresses, her companions become tipsy. Their conversations turn racy and their moods relax. They refill their glasses, reveling in a little buzz. Not so for Elizabeth. Before her first glass is empty, she experiences a fast flush response. Her face turns crimson, her heart begins to race, and her head starts to pound. Worse still, she soon feels the need to vomit. How can people respond so differently to alcohol? Well, it comes down to a difference in a single base pair in their DNA. A single difference that can influence dramatically a person's behavior, digestion, respiration, and general ability to function. The base pair change leads to the production of a non-functional enzyme, and the lack of a functional version of this enzyme leads to physical illness. Let's look at the details. When we consume alcohol, our bodies start a two-step process to convert the alcohol molecules from their intoxicating form into innocuous molecules. Each of the two steps is made possible by a different enzyme, whose assembly instructions are, for most people, coded in their DNA. Fast flushers such as Isabella complete the first step of breaking down alcohol, but not the second because they carry defective genetic instructions for making aldehyde dehydrogenase. This is the enzyme that makes possible the second step of the process. A poisonous substance subsequently accumulates, and the symptoms of the fast flush reaction are due to the substance's toxic effects in the body. Approximately half of the people living in Asia carry a non-functional form of the gene for aldehyde dehydrogenase, a mutation that may confer a greater benefit than harm. In a study of 1,300 alcoholics in Japan, not a single one was a fast flusher, even though half of all Japanese people are fast flushers. The minor change in the genetic code that makes alcohol consumption an unpleasant experience may be responsible for the lower incidence of alcoholism among Japanese and other Asian people. In many other cases, the link between a particular defective DNA sequence and physical illness is equally direct. Recall when we talked about Tay-Sachs disease. In Tay-Sachs disease, an individual inherits genes with a mutation that causes an inability to produce a critical lipid-digesting enzyme in their lysosomes, the cellular garbage disposals. Because these organelles cannot digest certain lipids, the lipids accumulate undigested. The lysosomes swell until they eventually choke the cell to death. This occurs in numerous cells in the first few years of life and ultimately leads to the child's death. Although the details differ from case to case, the overall picture is the same for many, if not most, inherited diseases. The pathway from mutation to illness includes just 4 short steps. In step 1, a mutated gene codes for a non-functioning protein, which is commonly an enzyme. In step 2, the non-functioning enzyme can't catalyze a particular reaction as it normally would, bringing the reaction to a halt. In step 3, the molecule with which the enzyme would have reacted to convert it to another substance accumulates, just as half-made products would pile up on a blocked assembly line. In the 4th step, the accumulating chemical causes sickness and/or death. The fact that many genetic diseases involve illnesses brought about by faulty enzymes suggests some strategies for treatment. These include administering medications that contain the normal functioning version of the enzyme. For instance, lactose-intolerant individuals can consume the enzyme lactase, which for a short while gives them the ability to digest lactose. Alternatively, lactose-intolerant individuals can reduce their consumption of lactose-containing foods to keep the chemical from accumulating, thus reducing the problems that come from lactose overabundance.